This one. A couple of buttons. All right. Okay, so let's talk about a couple of things before we get started, all right? And there's some terms in physics that have special physics meanings that are maybe a little bit different than the way you think of them. Two of those words are work and energy. So I want to make sure we understand what I mean when I say work. Okay, and just to be clear, I'm going to draw work with a capital W to distinguish it from weight or omega. So in physics, work is this concept that we're going to use capital W. It relates somehow to force and distance. The most general way of writing that, and we're on page 3, most of this is written down for you, the integral of force dotted with differential displacement. So it has to do with force and the direction you're moving, and we would say this force dot displacement, force dot ds. To make clear, this is a dot product between two vectors. Now, in practice, what does ds mean? That's it. Oh, go ahead. What were you saying?
With respect to time? Or
No. What does ds mean in mathematics? Arc length.
oh,
So if you're traveling along some arbitrary path like this, ds would be how much of the x and y. So you could think of it as being like dx in the I hat plus dy in the j hat plus dz in the k hat. Right? It's some amount that you're moving in the x, y, and z direction. And it's ds, so it's a tiny amount. So that's why it's a tiny amount in the x, y, and z. Is that okay?
yeah.
Now, for me, I like to think about this helping me do this integral. Because look at this. If I put this in here, check this out. I could actually do this integral a different way. It'd be the integral of the x force with dx plus the integral of the y force with dy, etc. Now take a second before we get ahead of ourselves. See if you agree with that. The idea is the dot product, right, gets rid of the i's, because the I dot I would give me the x component, and I dot I equals 1. So the I dot I term gives me that first part of the equation. This is from the two j hat terms, and this is from the two k hat terms. We're not doing cross products. Remember, dot product, I hat dot I is 1. I hat cross I is 0. Is everybody okay with that? This is just some math. Okay? Think about this though. Now I don't have to think about this crazy ds vector, because what I can do is I can take something and I can split a force into x, y, and z components, and I can say, look, how much did you go in the x? Integrate the x component times the x motion. Take the y component, integrate it with the y motion, right? And so the idea is then you don't have to know what ds is, you don't have to know about arc length, and we don't have to think, right? If force is constant, check this out. I'm just going to tell you. I'm going to write it like this. FD cosine of some angle. In particular, if your force points this way, I'll explain what D means right here. If you have a force and you know that there's a displacement while this force is in effect, we could get, and that force is constant. If all of these things are true, right? If we have a force, there's a displacement, there's an angle between them, and the force is constant, then we could get the work with this equation. To be fair, this is the one we're actually going to use the most, because for most of our FBDs, most of our forces are constant. Not always true. And that's why we've got the other method. We'll do that at the last half of class. Is that making any sense? Okay. Work. Now you may be saying, okay, fine. This is just, right now, it's just a weird abstract thing. But I want to introduce another concept, kinetic energy. When I think about energy, I like to think about something that has the ability to inflict pain. What I mean by that is the more energy something has, the more pain it could inflict. For example, a rubber band. If you stretch it a little bit, it inflicts a little bit of pain. If you stretch it more, it inflicts more pain. Therefore, I know a rubber band that's stretched a lot has more energy. If I drop a rock on my head, it's going to hurt more if the rock has more mass. So mass must have to do with its gravitational energy, things like that. Okay, kinetic energy, when you hear the word kinetic, that makes me think about motion. K is the symbol we're going to use. The equation for this is 1/2 mv squared. In this case, this is mass and this is speed. K is the kinetic energy. So think about this. A bullet can inflict a lot of pain. Now, bullets don't have much mass, but they do have a lot of speed. And you can see that that speed getting squared, this helps me understand why something as tiny as a little bullet could kill me, because it has so much energy. It has to do with speed squared. So for me, that helps me remember that. So far, so good. At first, these two things could not look more different. We're talking about work with this weird integral, with arc length, with vectors, and here we're talking about speed. Somewhere at the bottom of your page there, see where I said deriving the work energy theorem there? I've got the derivation, so I don't want you to take notes. I want you to watch on the whiteboard, knowing that the derivation is right there. You know what I'm saying? I'm going to do the exact same derivation, so just watch so you can see it live. Let's check it out. Work is equal to the integral of force dot dx. In 1D, let ds go to just dx in the I hat. Is everybody okay that we could just do something in one dimension for this simple case? I am. Good. Thanks. Okay, so work is equal to f subscript x in the I hat dotted with dx in the I hat. Then we're going to go from some initial value to some final value, right? Okay. Well, in this case, look at this. I hat dot I hat is equal to 1. Now I get work equals the integral of f sub x dx from initial to final. Great. At this point, I want to rewrite force. What's the most popular law that we've got in physics? F equals ma. Okay, so work. And again, this is all written down for you. I'm going to stop writing the initials and finals for a while just because I'm lazy. What's another way you could write acceleration? How does that relate to velocity?
V squared.
I was thinking dvdt. You're doing another one too, which is good. Okay, yeah. Okay. I'm going to choose it this way because then I can write it like this. Work equals the integral of m like that. Now you might not know this, but in math class, once you get to what are called differentials, you can flip the order any way you want. So I can move this dx over to here and switch it. Well, what's dx dt? V sub x. You see it coming together now? Isn't this fun? Well, what do you, whoops, this is ddx now, right? I switched the order of the differentials. Look carefully here. We switched these two. See it? So now we switched from an x integral to a v integral. That's totally legal. So wild. But what do I get when I integrate this? Let's say mass is a constant. Huh. See anything familiar there? Now I'm going to stick back on my limits. Look at this. It's equal to 1/2, I'm going to get really lazy now, v final squared minus 1/2 mass the initial squared. Or work equals change in kinetic energy. Got it? At first, this seems totally unrelated, but we see that work and kinetic energy are clearly related. If you're wondering why someone would make up this nonsense concept of work, it's because it relates to kinetic energy. Here is the deal. How many vector signs do you see in this last line? None. We can do some problems without having to do vectors. So the trick is, it turns out we're going to learn a process for calculating the work with these integrals or forces or distances or whatever. And then we can use that to learn about the speed of objects without having to do FBDs, then kinematics. So basically, we've got different tools that we're learning. We've got forces, we've got kinematics. This is a new tool, work and energy. Got it? All right. Something I might mention here, and maybe I'll go back to this board to do it. I'm going to be a pretty lazy person sometimes. Here, I want to point out, where did I say it? Somewhere here. It's actually a displacement, right? Because if this is a vector. However, this term right here, we're often going to call it the distance. And here is why. For most of these problems, we're not going to have this thing reversing direction, like going forwards and reversing direction. I guess what I'm saying is watch out if object reverses direction. Did that make any sense at all? We saw many times this semester that distance and displacement are not synonymous if something reverses direction. So if that is the case, we'd have to do two problems. One while it's moving forwards, one while it's moving backwards. Is that enough on that? Do you know what I'm, yes?
Or in other words, just look out for the hat symbols, if that helps.
What do you mean? Say again?
Because notice on the tiny displacement has a hat symbol, whereas distance does not.
That's right, that's right.
It represents a magnitude.
Well, I guess what I'm saying is, imagine you're doing a problem where there's a zombie and a block and it goes up the ramp, but then comes back down some.
Yeah.
Then you'd want to split it into a stage where it's going up the ramp, do all the problems, then down the ramp, do it. Got it?
Yeah, that's what I was trying to play.
Okay, okay, I got you. Yep, you're good. All right. Take a look on the next page. I've done some math there. You can kind of see some examples. I'm going to go ahead and do that example on the board once I erase. Okay. Erasing. So in this one, this is, I think, just called example page 4. Is that right?
Yeah.
Okay. There's a block. There's a floor. And then there's a force off at some angle. And there's some tension. I think it's 12.0 newtons. There's some angle here. I think I said theta equals 10.0 degrees. And then this block is going to slide for some distance equals 3.00 meters. Okay. So we can get the work. And sometimes what I'll do in this is I'll say work done by tension. I'm on the right way. Okay. Work done by tension. So I'll use a subscript to indicate which force I'm talking about. For example, in this case, tension would equal, well, is this force constant? Yes or no? It is. It's a number at a fixed angle, so it's a constant. I'm going to use force, distance, cosine of angle. In this case, the force is 12 newtons. The distance is 3 meters. And again, here it's okay to use distance and displacement interchangeably. And we got a cosine of 10 degrees. In this problem, it's very easy to see all three. It's just a practice one. What did I get? 35.5. What are the units left over? I just punched this into my calculator, nothing fancy. What units are left?
It's times a meter.
The Newton meter is the name of a unit. However, we don't like to use that unit. We're going to rename this unit. 1 joule or 1 J equals 1 Newton meter. So the unit of work is called a joule. We're going to rename this right here a joule. 35.5 joules. It's a real gem of a unit. Okay. So far, so good? Now I know that seemed, well, this is the easiest way to do this one. I'm going to show you the other one. Just trust me, there's a reason to show you a different way to calculate. This is one style of calculating it. I want to show you the other style. Right? This is the other style we could use. And again, because it's a constant force, I can just work this out. And at first this may seem dumb, but later on we may actually use this. Help me out. How much of this force is in the z direction? None. How much does this block move up and down? So we don't need this, right? So even though this looks a little bit more complex, it very rapidly becomes easy. What's the x component of the force? 12 newtons cosine 10 degrees, right?
Yeah. Yes.
So there's f sub x. Well, how much is dx in this problem? How much is delta x, I mean? 3 meters, right? Do you agree you get exactly the same math, maybe rearranged a little bit, but same numbers, right? So remember this cool trick. If you get lost, maybe you're not sure if you feel comfortable, try splitting the force into components And obviously, this method is tremendously convenient when something's only moving in the X, or only moving in the Y, or only moving in the Z. It's also very easy if the force is only in one direction, right? What if you have some force that maybe the particle is moving in 3D, but your force is only in the X direction? Then all you have to do is get the force times only the X motion. I don't know, is that making sense why this might be useful? It's handy because a lot of times, a lot of parts go to zero. Enough said?
Yeah.
All right, all right. Great. Let's go big picture before we do the next problem, right? This is the whole point of this. Oops, I want this board. Come on. There it goes. Okay, here's the deal. If you could get this one thing out of today's lecture, that's pretty good, okay? You don't have to write this down. We do an FBD, we write some force equations, get AX, AY, AZ, do kinematics. Good to go, right? So when we had problems and maybe we wanted to find the final velocity of something, one of the things we could do is we could do FBDs, figure out that, right? Do you agree we could in theory do this? You could do forces to get an acceleration, then use that with kinematics, right? That would work. New style. Get out of the way. It's just a little bit different. And to be fair, right now, you'd probably feel more comfortable doing this because you've done it a lot. But what is supposed to happen is we learn this new style and you realize there are some problems. This is so much faster. It's a new tool we're learning. Good? Now, to be clear, work net equals work done by the first force plus work done by the second plus work done by the third, plus all the way out to all of them. You know what I mean? It's just the network from every single force in the problem. So what you could do is, you could get the work done by tension, the work done by friction, the work done by normal force, the work done by mg. Add those all up, it's equal to 1/2 mv final squared minus 1/2 v initial squared, and solve for something. That's it. Good? Okay, okay. Let's try 7.1. 7.1 is a little bit long and a little bit boring, but it's actually got a lot of the confusing parts all in one problem. So we're going to do 7.1 next, okay? I'm going to erase the board. I'll leave this open for a minute. You can start reading 7.1, maybe do your FBDs, force equations, just to kind of get a feeling for it. Getting the board ready over here with Zoom. Guess if you haven't figured out, I know that there's no more math required. I figure I'm just going to keep rolling with mine for a while, at least for a couple more weeks. Doesn't bother me that much. It's just physics class, but so I figure if you're not sure if you're sick or you know whatever, if you think there's a chance and you're not sure, just put on a mask. Seems reasonable to me. All right. 7.1. Yeah, and I figure I'm right. I'm the one that's exposing everybody to each other more than all the rest of you. So I'm going to keep mine on that way. you don't have to worry about me coming up to talk to you. All right, anyways, 7.1, we got a mass. There's a block here. Somebody tell me one force acting on this block. MG, everybody likes MG, but it's a good one. Okay, what else?
Normal force.
Normal force, which way? Show me with your hand. Yeah,
Perpendicular.
perpendicular, excellent. What else we got? Is there the weird force on this one?
Force to the right.
Is that capital F?
Yeah, capital F.
What else? Is there possibly friction or not?
Yeah.
Which way is friction going to be? This thing's, does it go up the plane?
Yeah.
Okay, up the plane, so parallel the plane down. Okay. Something like that. Now, this is not an FBD because technically it's not separate, but it's pretty close. Is this thing accelerating or not? Do we know? Is there any clear indication if it's accelerating or not?
Sliding up the.
Sliding, but we don't know if it's accelerating, do we? Ooh, part H says starts from rest and then it picks up speed. So if I skip to part H, it says it's starting from rest and speeding up. So I think it's going to accelerate up the plane in this one. But if you didn't know, a trick is just assume it's accelerating up the plane. If it's not clear, it's better to assume something is accelerating because you could always set A to 0 later. Basically, don't assume acceleration is 0 unless you know acceleration is 0. Did that make sense? Assume acceleration is present unless something indicates otherwise. We'll just make that our X and Y. Why is this convenient to use that? What's the advantage of that coordinate system versus just a standard?
You only have to arrange the force.
Yeah, we only have to split up 2 vectors instead of 3. Remember the acceleration, we might have to split up 2, right? So fewer vectors to split up is good in my book. Anybody see any angles? What's this angle? 90 minus. So what's this angle in here?
Theta.
Theta. So what's this angle? And this one? Theta. So we got all our angles now, agreed? Is this correct, what I'm doing right here? No. Looks better, the right angle opposite the hypotenuse. All right, how about this one? Is this correct? Is the right angle opposite the hypotenuse, opposite the original vector? So that one's okay, agreed? So even though this isn't a free body diagram, it's so close, I'm going to go ahead and use this one. The only thing I didn't draw, or I included the ramp. I'm not supposed to include anything else, including the ramp. But here, I kind of like this because it helps me find the angles better. Agreed, opposite, adjacent. What's this component right here? F cos or F sine? Sine, which makes this F cos. Right there. Everybody okay with that? Okay, okay. Let's get some force equations here. This is hopefully all reviewed. In the X direction, what's the force equation? Anybody feeling brave? Positive or negative for F cosine? Okay, what's next?
Negative friction. Negative mg side. I think that should be it.
Okay, so all that equals,
Alright.
okay, how about in the y direction? Somebody else,
Normal force.
positive or negative?
Positive.
Okay, what else?
Minus F sine theta.
Whoops, that's green, isn't it? Sorry. Yes, I agree, minus f sine theta. Good, anything else?
Minus mg cosine theta.
Equals?
0.
Yep. Why does it equal 0 in this case?
No acceleration upward
Yep,
or downward.
yep. Excellent, nice job. Okay. What frictional condition applies? Do I use F equals mu static, F equals mu, F, do I say F equals mu static N, F equals mu kinetic N, F less than mu static N? Kinetic, right, because it's actually sliding. Nice job. So I know that the friction is equal to mu kinetic times the normal force for this problem. Because sliding, right? All right, nice. I think we've done part A. Part B says, give me the normal force. Well, which equation should I use to get the normal force?
Why?
Why? Yeah. Part C, get the frictional force. How do I get the frictional force in this problem? You could use the X one. Do we know the acceleration though? So you're right, we could use this, but it would introduce an unknown. Is there another way? Yep. All right, now we're supposed to be doing this new thing, remember? Right now it feels like we're doing the same old thing. This is the setup. We can draw an FED and we can learn about these forces. Now we know the size of the force to shove into the work equation. Remember the work equation is force times distance. Well, now I know the size of the force for those two. So now let's start doing something new. Part D, work done. Work done by, what did I call it, capital F? Yes. Now, for this problem, all of these forces are constant, so I don't need to do any integrals. So I could just say it's F times the distance times cosine of some angle. Okay? I highly recommend you pay attention right now to save yourself a lot of headache. The trick to me for getting these problems right is to immediately draw a tiny little picture showing only this force and the displacement. Which way is this thing being displaced? As it goes up the ramp, it's this way. This helps me figure out the angle. And I believe in this problem, they said D is equal to L or whatever, right? They said the distance it moves is L instead of D for some reason. Who cares? Now you can help me. Is this angle going to be theta, 90 minus theta, 0, 180, 90? What do you think? It's theta. You can see it in the picture. It's the same as the incline of the ramp, right? Right here. This tells me angle equals theta for this force. And when we finish this problem, you're going to see every single force is going to have a different angle associated with it. And the trick is, when you see a problem, just because I say theta in the problem doesn't mean theta goes in here. In this special case, theta happens to be the angle that goes in there. In every single other force, it won't be. Is that clear? Draw a picture, make sure the angle is right, then do your math. That's it. And you'll get this right every time. Okay, let's do this. In this case, that's just F L cosine of theta. No big deal. That one was really easy. They aren't always that easy. Okay. What is the next force we're supposed to get to work?
By gravity.
By gravity? Okay. Just a sec, I'm erasing the board over here. And I'll remember to change. Okay. I want the work done, and this is what part E, the work done by gravity. So it's force, distance, cosine of some angle. Immediately, I'm going to draw a picture, right? Which way is mg?
Straight down.
Straight down. Which way are we being displaced? What's the angle between them? What's this angle down here? That's 90. What's this angle up here? So it's 90 plus theta. That is weird, right? I don't like this way because now I'd have to know a trig angle. I'd have to know a trig function, right? This would work. It would equal mg L cosine of 90 plus theta. That would work. I don't like that. If I was coding it, sure, I would use it. Whatever. I want to show you another way. This is one, because it makes me so uncomfortable, I don't want to have to learn a trig identity. I'm going to use this way. Force in the y times delta y. Now, do you agree I don't need to worry about force in the x or force in the z for this particular force? mg is, that's why I'm writing it as force y delta y. Well, now help me out. What's the force in the y direction? Negative mg, outstanding, mg downwards. What is delta y? How much do you go up?
D sine theta.
L sine theta or D sine theta, however you want to look at it. Yeah. Do you agree the change in the y direction is right there screaming out in that triangle? And now, I guess I just learned myself a trig identity. Look at that. It looks like cosine of 90 plus theta is negative L sine or negative sine theta. Do you see it? These two must be equivalent. It's only valid if this equals negative sine. Wild. Isn't that cool? Personally, I like not having to know the trig identity. So I like knowing both styles. Enough said on that. If you are in the real world, Google it. Sure. This physics class, sometimes it helps to have some simpler ways. Just give me a thumbs up, thumbs down right now. Are you following or not following? Okay, for the most part. Okay, good. Let's do part F. The work done by friction. Is that right?
Yep.
All right. F D cosine of some angle. Okay. What's the next thing that I've done every single time? Draw the picture. Which way is friction? Show me with your hand. Yeah, and which way is the displacement? Other way? Okay, got it. What's the angle between? 180. You agree the angle is now 180? Sometimes theta doesn't even come into play, and this is one of those cases. So it's equal to friction times L times cosine of 180 degrees. What's cosine of 180? Negative 1. Did you notice the work done by the last two things is negative? Friction, which opposes the motion, does negative work. Gravity, which opposes the motion, does negative work. Oh, and that's off the screen, isn't it? Sorry, let me fix that up. So the work done by friction, sorry about that, Zoom. Friction's down the hill, displacement up the hill, 180 degrees. You get this equation. All right, great. It turns out, I'll summarize this in a minute, but things that oppose your motion do negative work. All right, that's cool. Well, so out of all this, work done by friction is, I think we figured out the friction was mu kinetic times F sine theta plus mg cos theta. I'll get out of the way. That was that, times L. Oh, and then it's got to be negative. Is everybody okay with that? That's the work done by friction. I just took this is mu kinetic times the normal force from our free body diagram. You look back at the free body diagram, that's where that came from. The minus sign came from the picture. This minus sign came from the 180 degrees. So this is the magnitude of the force, the distance. The minus came from the 180. Okay. Part G, the work done by the normal force. Well, displacing this direction, D or L or whatever you want to call it, the normal force is perpendicular to the plane. What's the angle between? What's cosine of 90 degrees? 0. What's the work done by the normal force? Interesting. We'll make a few observations here. Getting a little bit better framing on that. Can you still read the subscripts, Alan?
Yeah.
Okay, thanks. If a force opposes motion, the work is negative. We could see something else. If force perpendicular to motion, what's the work done? 0. These are two useful things to help check your work. Basically, if a force is perpendicular or close to perpendicular, you expect 0 work or almost 0 work, right? Only forces that have a large component parallel to the motion matter. Okay, and the other one is, think about this. If you're throwing a ball up in the air, does gravity help the ball go up or does it oppose that motion? As you throw a ball up in the air, It opposes that motion. So gravity would do negative work on the ball as it's going up. Now, what if I drop a ball? Gravity helps it go downwards. So when it's on the way down, gravity can do positive work. So it's not as simple as just saying gravity always does positive or negative work. That doesn't help. You have to think, does gravity go with the motion or does gravity go against it? If gravity goes with the motion, at least in part, you would say it's doing positive work. If gravity opposes the motion, like in this problem, we're going slightly uphill, gravity's got a downward tilt, get a negative work. Okay, is that good? So, all right. Cool. I think we're up to part H now, right? Run out of room. I need to come back over here. Come on now. So I know we've got this free body diagram. It hurts me to erase it, but I'm going to do it. By the way, this is about as complicated a problem as I could imagine. We just did the most complicated one I could think of. It's not that bad, right? You can kind of do it already. Okay. Check this out. Part G. Work net equals delta K.
It's part H.
Oh, part H, thank you. Okay, work net is delta K. In this case, that's the work done by the force, F, the work done by, what was next, mg, plus the work done by the friction, plus the work done by the normal force, all adds up to 1/2 mv final squared minus 1/2 m the initial squared. In this problem, I believe they said it starts from rest. Is that right? Yeah. What does that do for me over here?
Initially 0.
Nice job. Good. What are we trying to find here?
Final speed of the block.
Final speed. Now check this out. I'm going to put parentheses around this for just a second so all these look the same. Do you agree this term's gone? I could multiply 2/m by both sides. If I do that, I get 2/m times all these work terms. Almost there. Hang tight. And then I could square root it all. And that would give me the final. At this point, it's just plug in those long expressions that we just found in parts D, E, F, and G. In particular, like you could plug in that this is 0. This was that weird, ugly one. There's 2 other ones. Got it? And then you could group like terms. And I think in this case, oh yeah, it's just ugly. It just sucks. So let's leave it at that. I did the work in the solutions manual if you wanted to see it, but I think at this point you could plug in that, stick it in a computer, type in some numbers, make the computer calculate the answer.
So then the velocity will have like a direction too, or do we just say like the velocity?
Ah, that's a good point here. Let's see what did I actually ask for. I asked for the final speed. So he's absolutely right. Now, to be clear, speed should be positive, right? So that's why I didn't worry about the plus minus on the square root. But if I'd asked for velocity, I would say it's this value, that direction.
With the theta?
Yeah, so right, I guess if you really wanted to, you could say it's cosine theta in the I hat and sine theta in the j hat times that number would give you the velocity vector, but I don't want to do that. That's too hard for me to do. You know what, but that's how you would do it. It's not terrible. Good? Yeah. So usually in these problems, we just want the speed. Okay, this is your new toolkit, right? This is a new technique for finding speed that doesn't require kinematics. And at first, this may seem like almost just as much work, maybe more, but let me give you another example of why this might be useful. right here, you can see on this desk. And then on the break, don't forget to turn in your lab if you haven't already turned it in. But the idea is you can see, here's an example where the spring is doing work. And I'm going to teach you a method for handling the spring. Now, springs are much more complicated. As you stretch a spring more and more, what happens to the force? Does it stay the same or does it change? Changes. The more you stretch a spring, the more force is required. So even though this process we just did seems complicated, you could actually use that to handle problems like this where the force is changing. And now think about that. If the force is changing, the acceleration is changing, we can't use constant acceleration kinematics. So this new method that we have will work even when forces aren't constant. That's a big difference. It's a big deal. Does that make any kind of sense why we care about this, even though it looks harder? Okay. You guys bored out of your mind yet? Nope. Let's try 7.2. Discuss that with your neighbor. Talk to him as much as you want. 7.2. You're not doing the whole thing. It's just guessing the signs. Remember we were talking about whether work is positive, negative, or... Take a second to do that while I get the board arrayed. Okay. 7.2.
I got it. The top block is has no ability. So I would say top block would have no it's side object always flexible. I could just do a little demo of this. Or actually, it could depend on how that could also depend on the speed. If it's sudden or gradual. It's gradual. Yeah, it's set. Yeah. Well, it depends.
Okay, get on the right whiteboard.
Yeah, got it.
You got it? Okay, all right. So you had a second to kind of look at this one. We're trying to figure out if friction does positive or negative work on the top block. Is that our first one? Well, which way is the top block going to move? We know it's going to move this way. So we're looking at A, top block. right? So I know it's going to move this way. There's displacement. What direction is the frictional force on the top block? Is it to the right or is it to the left? If there was no friction, what would happen? Tell you what. Let's do it this way. Okay. Do you agree these wheels will give negligible friction? Oh boy. If I pull this book really fast that way, this tends to go off the back. Right? Yeah, oh, not whatever. I'll call in sick for the rest of the semester. Sorry, guys, learn it on your own. That would be so sweet, wouldn't it? For me. Oh, yes, but I can't, it's really hard for me to do this, but, whoa. I did so well today. All right, that's all that's for that demo. All right, you get the idea that if I pull this really fast and friction's negligible, the top one moves backwards relative to the bottom one. Therefore, friction is forwards. On top due to bot. Are you okay with those words? Right? Because the bottom is there, there's friction. On the top one, it's forwards. Work done is positive. Right? It's in the direction you're moving. It should tend to speed you up. If there was no friction, it would stay put. We live to fight another day. I just broke this in. That's nothing. B. On the bottom block, which way is the bottom block moving? That way. There's no ambiguity there, right? Which way is friction? There's no friction between the bottom. Is there friction up here? In fact, if the bottom exerts friction on the top to the right, which way does friction, which way does the top block exert friction on the bottom block? Newton's law, third law. F on bot due to top. Does that make any sense? I like to say it this way. It makes it, look, the bottom block frictions to the right on the top, or else it wouldn't go anywhere. Now I know frictions is not a verb, but it helps me. The bottom block frictions to the right on top. By Newton's third law, the top block frictions to the left on the bottom. What's the work done? Positive or negative? Got it? Now, is this frictional force internal? It's internal. So what do you think is true about the network on the system? Zero. Exactly. So the work done, I should say work internal. If you have an internal force, on the system, this is probably worth saying precisely. The internal forces do no net work on the system, right? Clearly, friction is doing work on the top block in the positive way. It's doing negative work on the bottom block, but does no net work on the 1-2 system. Is that enough on that? Sort of like internal forces, you could ignore them in FBDs. Internal forces, you could ignore them in work energy. That's why we're mentioning that. How would these answers change if I, instead of pulling the bottom block, I pulled on the top one? Take a second, think about it with your friends. Discuss with your friends. If we switch the applied force to the upper block, how would that change these answers?
There's still no friction on the bottom.
There's still no friction here, but there still is friction here and they still slide together. What are you thinking back there? What would it do? Yeah, it would flip the frictional forces, right? That's the only difference. If you pull on the top one has to drag bottom along with it. That means there'd have to be friction forwards on bottom, otherwise it wouldn't get dragged along. Then, so the bottom would have friction this way, the top would have friction the other, by Newton's third law. The works would still flip, but you'd still get zero total. Is that good? All right. Which friction condition applies here? This is just a bonus question. Is it F equals mu static N, or is it F equals mu kinetic N? Which one of these conditions applies here? It's not on the verge of slipping. Neither is the correct answer. No, man, I can't get this guy. It's actually F is less than mu. I didn't give you all three choices. Well played. So nice job. Do you agree? We don't see anything in this problem that says it's on the verge of slipping. If it's on the verge of slipping, this is true. Just because the top block is moving doesn't mean I use kinetic friction. It's not moving relative to the bottom. So this would actually be the correct one. Nice job. Nice job. That was just for fun. All right. 7.3, 7.4, those give you a couple ways to mix this up. I want to do one more fun one, and then we'll take our break. One more fun one, okay? 7.5. But this one trips me out. Your old friend, the car on a bank curve. Sure, this is exciting you to see this up here. But something's really weird about this problem. You'll see. Let's assume our car is going around with some constant speed v. Okay. This is the top view. Do a rear view. Okay. Got the center of our incline here. What's one force acting on this thing? I'll do mg this time. I took the easy one. Mg, that's a force acting on it. Any other forces? It's a car on a banked curve. Go ahead. Is that you? Oh. Normal force, yes. Sorry, let me give you a second to read it. My bad. Okay, you got a car. It's on a banked curve. It's angled. It's driving at the maximum speed possible without sliding to the outside of the track. It's on the verge of slipping, correct. So that tells me what? You static N? Wait a minute. This car is going really fast. Should we be using static friction for a car that's going really fast? Remember that long diatribe I went on last time? The point of contact with the road is not moving. Remember the tire, the bottom of the tire is actually not moving relative to the road. Otherwise you'd be doing a burnout. Okay, cool. So it's okay. I feel good. Nice job. Which way is friction? We're going really fast, we tend to slide out, so friction is, yes, down the hill. Remind me, which way is this car moving in this picture? It's going around this, like from the top view, it's going this way. So if this is the same instant in time, it would be going into the page. That's an X, right? How much work is done by the normal force? Why? It's perpendicular. Do you see velocity into the page, normal force is perpendicular. There's no work done by the normal force. What's the work done by the frictional force, however? Somebody else?
Negative.
No. What's the angle? Still zero. You see it? Isn't that weird? What's the work done by gravity? Zero. What's the work done by all of these forces? Zero. Is that a problem? The change in kinetic energy well, if we're going at constant speed, do you agree there's no change in energy either? So it actually makes sense. My point in showing you this was one, to practice with angles. Two, to show you that if you're moving with constant speed, net work must equal zero. Think about it. If you have constant speed, the change in kinetic energy is zero. So if you're moving with constant speed, there's no work. This is true for anything going around in a circle. So basically, circular motion problems with forces, we rarely use this technique because it doesn't tell us much. Everything's zero. Did that make any sense at all? Basically, this work energy trick will not be very useful for cars going around in circles or circular motion forces. So don't try to use that. Good? All right, all right. Should we take a break and come back? Seems like a good spot. When we come back, we'll handle non-constant forces. Up till now, everything we've been dealing with is constants. Let's take a short break. You can turn in your labs if you haven't already done so. I've got 5:39 on this clock. All right. Okay, so let's get back into it a little bit and let's talk about springs. All right. And maybe I'll show you a few things about springs that are kind of confusing with this example I have here. All right, let me get some of this clutter in the background out of the way. Okay, so hopefully you can see this. It's not too much junky. All right. Now in this case, I've actually got two springs, one on each side. We're probably going to simplify this in a minute to just one spring, but just so I can talk and have my hands free with this thing balanced, I'm going to put two on here for right now. So one of the things that's tricky about springs, as we discussed earlier, right, as I stretch this more, there's going to be more tension in the spring, the force is changing. So depending on the location of this, depending on the value of X, the force is different. Now in this case, we see some wild motion here. Eventually this is going to settle down. And I want to point out this spot. Right here, do you agree that the block is in equilibrium, meaning no net force? Is this thing accelerating right now? No. I mean, I guess you could say it's accelerating towards the sun as it orbits the organic. Okay, so yes. Right now, assuming we're in the Earth rest frame, right? So the up normal force, mg, and these two springs are balanced. But I want to point out, do these springs have force right now in them?
Yes.
Yes, they're stretched. To be clear, this point right here, the spring is not stretched. Now with a single spring, horizontal, not stretched, equilibrium, same thing. However, in many cases, with a two-spring system or with a vertical system, at this point, we see it's possible something could be in equilibrium while also being stretched. So equilibrium means forces balance. Equilibrium means forces balance, not spring has no force. Seems obvious, but it's not necessarily obvious. Here's another case. In this case, probably can't see the spring too well there. Let me zoom in a bit. Let me just go 6. Maybe you can see it a little bit better now. So in this case, I can let this thing kind of come to equilibrium. Right about there. This mass is in equilibrium, but the spring is obviously stretched. Agreed? So here's a case where that is the unstretched length of the spring. This is the equilibrium length, and they're different. Good enough? So I want to use these words correctly because I remember when I was starting, they were very confusing to me, and I would use unstretched and equilibrium interchangeably. That's only true in like one case. The only time you can use unstretched and equilibrium interchangeably is essentially this one, where you've got a horizontal situation with a single spring that's not stretched. It's also in equilibrium. This is the one case where unstretched and equilibrium are the same. That said, let's learn some more about springs. Or any questions while I've got that there? Maybe I'll mention one other thing too. Just because you have no force doesn't mean you have no motion. In particular, that's approximately the center of the equilibrium, right? Where is this thing moving the fastest? Which point? On the right, on the left, or at equilibrium? Look at it carefully. Right here, where the force is balanced, it's actually moving the fastest. If I slowed this down, you could probably agree with that even more, right? Think about it. When it gets all the way to this edge, it stops. when it gets all the way to this edge, it stops. It's actually fastest in the middle where there's no force. Where do you think the force is the biggest? At the ends, right? So notice when there's no motion, when there's no velocity, the force is biggest because you get the most stretch, right? So this is a complicated situation. All right, now I swear we're going to work. Okay, I'm just trying to give you some intuition for springs. They're really kind of fun, but tricky. All right. Crash course on springs. So before we do any problems, let's try and just give you some facts about springs. Springs, okay? This is the standard textbook definitions you see. Some springs could be compressed, some can only be stretched. If you need to see both, I've got some in the back, I'll bring them out. The key for this, in understanding the force, we need to talk about the amount the spring is stretched or squished, compressed or stretched from its unstretched length, right? That was the whole thing. If I wanted to, I could say it's like this. Okay. For reasons that probably seem pretty obvious, it is convenient, but not required. It's just so much easier. X un means unstretched length. Sorry if I didn't make that clear. The unstretched length I'm calling X un, right? And just imagine how convenient it would be to set up your coordinate system such that that parameter is 0. Then we don't have to deal with that subtracting X un all the time. What's that?
What if it goes to a negative?
I'm going to go through the plus minus in just a minute. So yeah, just give me a second. If this is the case, then I'm going to draw a picture so we can think about pluses and minuses. Do you agree, though, that if I just set this x un to 0 in the coordinates, I can just change this delta x to x, and it's a lot easier for me to work with? So what I want to do is basically set this as x equals 0, and I want that to match x unstretched. So wherever x equals 0, that's my coordinate system basically. I want to set x un to 0 there. So that's the position where the spring is not stretched. Okay? And in this problem, this would be x, a vector, from there to the right. And imagine if you had your spring. Notice the block moves over this much, so the spring got stretched x. Agreed? Well, look at the force vector. If x is a positive number, what direction is the force? Positive I hat or negative I hat? If x is a positive number, the force is to the left. Well, let's do the other case, which I think is what you were asking about. Give me just a second. You're saying, what if you squish the spring? What if you compress it? In this case, notice x would be less than 0, right? Because it's some number to the left. What would happen to the force? Is that what you were wondering about?
Yeah.
And so this works, and it's complicated. Springs are complicated, so it's easiest to handle this thing with a vector. You tell me the position of the block. So let's be clear here what these symbols mean now. We kind of get a feeling that the signs are going to work out, but what do these symbols mean? X equals position relative to x un. It's the position. It's not the distance, right? It's a position vector. And that's why we handle the plus minus okay. K is a constant. It's a constant for a spring. So knowing physicists, we're really creative. We call it a spring constant. What are the units of the spring constant? What are the units of F? Newtons. What are the units of a position? So what does this have to be? Newtons per meter, double check, it works out. So the spring constant has units of newtons per meter. Sometimes you'll see this called stiffness. The stiffer the spring, the bigger the spring constant. So if you have a big number for K, it's a very stiff spring. It might be used as a shock on your car. If you have a very weak spring, like these little ones here that I was playing with, this particular one right here, this little crappy one that we were using earlier, I think this is like 3 or 6 newtons per meter. Now think about that. If I apply 3 newtons, if this is a 3 newton per meter, if I apply 3 newtons, I can stretch it a meter. Got it? That's what the newtons per meter. It's how many newtons are required to stretch it a meter. Now, to be fair, some people use how many newtons to stretch it a centimeter or whatever, but you could do the conversions. It's basically how many newtons to stretch it some known distance. A big K, it takes a lot of newtons. It's a stiff spring. Is that enough on the units of K and stuff like that? All right. We're trying to learn about work. Let's do that on the next one. Look at 7.6. That's kind of a summary of everything I just said. Ooh, there's one more thing. Ooh, crap. We'll do that when we get there. Okay. We already did part A. Units correct. Remember we just checked the units? In part B, it says, determine the work done. I want the work done by the spring going from 0 to 6 centimeters. Is that right? Yes. Okay. I think it says 0 to 6 centimeters I hat. All right, so in this picture, I'm going to draw a little picture here. We're starting at 0. I'm assuming this is also x unstretched. That's what we were talking about just for half an hour there. Now my goal is to stretch it and go over to here. And in this case, I want x final to be 6 centimeters in the I hat. Okay. I need the work done. Is the force constant? As you stretch this spring, is the force going to remain constant, or is it going to get bigger and bigger? It's going to increase. So I can't just use FD cosine theta. Point being, this is not valid, right? I can't use this anymore. This is only valid if the force is constant. Darn it. Can't do that. What I can do, how about this? I could do this, f sub x dx. Or maybe you want to see it the other way. We could do the integral of f dot ds. That was the original version that we said. Let me just walk you through this, right? That's the integral of f sub x in the I hat dotted with dx in the I hat. The idea is in this problem, ds, it's moving to the right. So a small displacement to the right, we usually call that dx in the I hat. So this is what happens to ds. What's the equation for the force due to the spring? Get it here. It's negative kx vector. Well, isn't that the same thing as negative kx in the I hat? So basically, f sub x, what's f sub x for this problem? Everything except the I hat, what's f sub x? Is it kx? No, what's missing? It's minus sign. I know this seems cheesy, but I'm trying to highlight this minus sign. Look, sorry, am I losing you guys? I feel like I'm losing you. Let me just reiterate this. Force subscript x just means tell me everything that's in the x direction, but leave off the I hat. It's like our old vector trick, right? You give me the x component of a vector, you don't write the I hat with it. But you could include the minus sign. So I'm trying to emphasize here that when I write this way, this is the standard math way of writing it. We get this equation that looks like this. What's I hat dot I hat?
That's one.
That's 1. So that's why when we see this, we should still include the minus sign when I bring it up here, because the minus sign is the x component. I don't know. Is that making sense? I'm trying to emphasize why I should include the minus sign. If I did a bad job, sorry, let's move on. Okay, what do you get when you integrate that? K is a spring constant. Pulls it out, we get a minus k. X dx is
X squared over 2.
x squared over 2, evaluated at initial and final. So let's actually work this out. What was the number for k in this problem? Was it 40?
Yep.
Newtons per meter? Is that right? Yep, okay. So what's the work done? It's minus 40 newtons per meter times, oh, I guess divided by 2, I can factor out that, x final squared minus x initial squared. Be careful, it's not x final minus x initial quantity squared. To be clear, you have to do each one squared and then subtract. It's not equal to, this is wrong. This is not right. You can't just do the subtraction and square it, even though that'd be easier. Okay. All right, what's x final in this problem? Yeah, do you see a problem that we're going to have?
Centimeters.
Centimeters and meters. Ugh. So what should I plug in for x final so that it matches? 0.06 meters. And then x initial is, oh, that one's easy. Got it. Okay, so let's punch in these numbers really quick on your calculator. Just do it. What's going to be what? Negative 20 times 0.06 squared. I got negative 72 milli what? What are the units? Yeah, joules. Look, it's going to be newtons per meter times meters squared. It's a newton meter. That's a gem of a unit. But shifting it, that's negative 72 millijoules. Does the sign make sense? If this block is moving this way, somehow, some way, maybe I pull it, should the spring help it move that way, or should it oppose the motion as it moves this way? As I pull this here, is the spring helping me move it, or is it hurting me? It's hurting me. So the work is, the sign makes sense. Work is opposing my motion. That's why it's negative. So far, so good? All right. Here's a fun question for you. If I stretch it another 6 centimeters, so let's say we go from 6 out to x final equals 12. Oops. If I go all the way over to 12, do you think I'm going to do the same amount of work going from 0 to 6 as 6 to 12? Do you think it will be more work, less work? Take a second, discuss. Is it going to take more work to go this far or this far? It's the same distance. Discuss with your neighbor. Which takes more work, or is it the same to go from here to here or from here to here? I'll erase this board. What do you think?
So the initial is 6 centimeters now? Is that what you're trying to say? Write it down.
Would the initial still be at 0 or at 6?
So I'm saying compare 0 to 6 to 6 to 12.
Oh, okay. Gotcha.
Sorry, yeah. I put the extra pause in because otherwise I'm saying 2 a lot. Yeah, you agree it would definitely be more if you went from 0 to 12?
Yeah.
But what I'm curious about is how does 6 to 12 compare to 0 to 6? All right, let's take a look at it. If you wanted to know the answer and you didn't want to think, what could we do? Plug in the numbers and just change the limits on the integral, right? If we do the work from 6 centimeters to 12 centimeters, the limits are 0.06 meters to 0.12 meters it's the same equation inside, so basically it's the same answer. We're gonna get negative 40 newtons per meter over 2, but now we're doing, what was it? 0.12 meters squared minus 0.06 meters. Okay, what do you get? Punch it in. 0.12 x squared minus 0.06 x squared equals some number. And then what do? Multiply by negative 20. Is it more, or is it the same, or is it less? It's huge. Isn't that interesting? You stretch it the same amount, but because you're starting, it's tremendously different because it's all amount you stretch relative to unstretched. The farther you stretch a spring, the more force. So this is part of the idea of the resistance training of those bands, right? If you've ever had one of those bands that you step on and you do curls or something like this or whatever, the idea is the more you stretch it, the more you have to exert. So it can cause you to have a larger force at a different spot in the motion, and it's a fun way to cross train or something. I don't know. Point being, yeah, 3/4 of the energy occurs in the last 6 centimeters, 1/4 in the first 6 centimeters. Very unusual. So it's a lot easier to start stretching the spring than it is to finish out the last little bit. All right. Does the minus sign make sense? Yeah, we're opposing the mode. Okay. You feel like you're starting to get springs? Oh, I've got one for you. This is a fun one, part D. So I think this was part C, wasn't it? Sorry, I forgot to mention.
Yeah.
Where do we start on this one? It's at 12. Okay. Okay, here's our unstretched position, which we're using as our coordinate, right? This is the unstretched position, and we choose to set that as the 0 of our coordinate system. We're going to start with the block way over here. We're going to start with it at x initial equals 12.0 centimeters I hat. And I'm going to let it come over here to this point. Sorry if it's not perfectly drawn here. At this point, x final equals negative 12.0 centimeters I hat. So I go from 12, right? I pull it over here. I release it from rest, and then it comes over here. How much work was done by the spring? What do you think?
You can't, like, my assumption was that just double it never, but you can't double it because it's different based on how close it is to the unstretched. Worse, you can't just double it.
Okay, yeah. What were you saying?
The work net is 0.
You're saying work net is 0. Well, let me ask you, if work net is 0, what should be the change in speed? How does work relate to kinetic energy? Work equals change in it. If there's no work done, that would mean it has to have the same speed. Do you agree? If I pull it over here and let it go, how fast is it moving when it gets to the other side? Should be 0, right? Isn't that exactly the same as this problem right here? Right? We're starting right here. I can pull it to this side. Right? And now when it gets to the other side, it comes to rest for a split second from here over to here. There's been no work done. Well, wait a minute. think about it carefully. The spring is doing positive work as we reach the equilibrium position right here, right? As you go towards equilibrium, the spring does positive work. Then as you pass equilibrium, the spring is opposing it. This one's dominating. So then you do negative work. And the trick is you do the same amount of positive work going towards equilibrium as you do negative work going away from it. Did that make any sense at all? Give me a thumbs up, thumbs down if that made, just be straight with me. It's okay to tell me it was terrible. Halfway? Yeah, one last time, right? You start here at rest. The force is this way on this side. The force is this way on the other side. Your displacement is this way. Your displacement is this way. On this side, the spring's doing positive work. On this side, because the forces switch directions, you do negative work. Did that help? You got it now? Ish? Pretty cool. All right, so we've seen a couple of weird cases for objects going in circles, or for this weird case where the force can change direction. Sometimes work is equal to 0. It's a very strange problem. All right. I'd like to do 7.7 right now. Okay, 7.7. I'm going to erase the board here. You guys take a second to look at it. 7.7. There we go, close enough. All right, 7.7. Where am I? Where am I? All right. Before you get bent out of shape about this force, if you recognize what's stupid about it, wait till the end, okay? In particular, part F says this is a stupid model. Why? But let's forget that for now. We're told we have a force f sub x. Okay, this is supposed to be, imagine you have a bullet here sitting in the barrel of a gun. Okay, for right now, I'll assume the coordinate system's right here. Okay. And the length of this gun, I think, is capital L or something. The length of the barrel. There's a lot we can learn by this problem, even though it's kind of silly. And I'll explain why it's silly at the end. If you wanted to get the work done, oh wait, what does it say to do first? Get the units. I want the units of alpha. Remember this trick from test 1? How do I get the units of alpha? You can split it up. I can get the units of force equal the units of this term equal the units of that term. So obviously alpha doesn't equal x and f sub x, but the units have to match. So from this, what are the units of alpha? What are the units of f? Over the units of x, which are? Similarly, what are the units of beta? Yeah, I think so.
It's supposed to be squared, not cubed.
Cube? Oh, squared?
Yeah.
Thank you. It's a good time to catch it. Thanks for saving me some headache there. So then in this case, it would be newtons per meter squared, I think then. Is that right?
Yep.
Is everybody okay with that? Why would we ever do this? Here's why. If we check the units at the beginning of the problem with the equation that the instructor or somebody else gives you, we now have a way to check our units at the end of the problem. If we don't know the units of these unknown constants, we can't check our work later. Got it? Always do this step first, always. It's going to be on pretty much every test. I'll write some equation here, and I'll say, like, check the units, will you? Okay. B. We're trying to get the work done as the bullet moves. So somehow this bullet moves. Let's get the work done by this force. Is it constant? Is the force going to be a set value, or is it going to change as the bullet moves? Is it going to be the same, or is it changing? Changing. So can I write FD cosine theta, or do I have to integrate? I have to integrate. Got it. What are the limits on my integration for this problem? What value of x does it look like we start at? 0. Where do we end it? Okay. Do you agree we can crank this out real quick? In this case, we should always check the limits. In this case, I think the 0 limit's going to drop out, but we should always check. Give me a second. Did I do that right, or did I screw it up? X squared over 2, x cubed over 3, right? Now, do you agree when you plug in 0, the 0 limit drops out in this problem? So it's going to be alpha L squared over 2 minus beta L cubed over 3, right? Yep, okay. Great. Was that part B? Yes. How could we use this to get the speed of the bullet as it leaves the gun? How does this relate to the speed? Work equals what? Change in, which we know is 1/2 that.
Yep.
So couldn't I just set this equal to that? And I could relate this to these parameters here. Maybe V initial is 0, maybe not. I don't want to go into that too much. Let's pretend V initial is not 0 for right now. Okay, so assume V initial is not 0. I can just rearrange this. You remember the old trick I said? You can multiply by 2 over m. If I multiply this by 2 over m, if I multiply this by 2 over m, and I multiply all of this by 2 over m, that cleans it up. Point being, we get something that looks like this. V final is equal to the square root of V initial squared plus 2 over m times alpha L squared over 2 minus beta over 3 L cubed. If you're wondering how I got there, I could show you later. Let's not focus on that. This is what I want to focus on. Up until this point, it feels like we're just doing math all day long for no good reason. Think, this is a time that an engineer or somebody that's designing a gun might be able to use this model to improve the gun's performance. Think, let's say these parameters alpha and beta relate to, say, the barrel size of the gun, or maybe the amount of rifling used, or something, right? These parameters could relate to something about the gun, or also the barrel length relates to the gun itself. You could use that information and try and adjust the design and see how that affects the final speed. And that's, I think, kind of interesting. In particular, if this is really the force, we could also say, well, at what point do I get no force? Right? Now think about this. For small values of L, which one of these terms is going to be bigger? If L is a tiny, 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 tiny number, which one of these is going to be bigger? How about this? If x is 0.0001, what's bigger, 0.0001 or 0.001 squared? Yeah, this term tends to be bigger when x is a small number, right? If you square tiny numbers, they get even tinier. So this might be a tiny number. This would be a tiny number squared, really tiny. So at small distances for small values of x, this term is big. It dominates, the force is positive. On the other hand, if x gets too big, this term wins, right? If I had x equals 10 billion, 10 billion squared is a lot bigger than 10 billion. So there's some special point in this force where the positive force that's helping push the bullet out of the gun is balanced by the negative force. So in this sense, you could say, oh, if I set the net force to 0, that gives me the over-under for telling me which position allows the positive force to dominate the negative force. When we do that, alpha x equals beta x squared. By the way, this is part E, or wait, no, part D. At what point is there zero force, right? Well, at this point, if we have alpha x and beta x, what do we get? Alpha equals beta x. X is something like alpha over beta. How can I check this answer? Let's check the units. Oh man, I wish I knew the units of alpha and beta. Pretty handy to have that. It's meters. This gives you an optimum barrel length. Does anybody see why this? Okay. That's it for this problem. If you have a non-constant force, you can integrate. If you have a non-constant force that has some constants in it, check the units so you can check your units. Then finally, in theory, we can hopefully use these algebraic problems to help design better equipment. That's kind of why you're in this class if you're an engineer. I hope that foreshadowed why you might do this. And I apologize if I didn't do a good job. Why is this force really dumb? Does anybody see why? I'll give you a hint. What's the value for the bullet that it starts at for x? So what's the initial force on the bullet?
Negative.
If x is 0, what's the initial force on the bullet? 0. So the bullet would never leave the barrel. Do you see this is completely stupid? But my point was trying to keep the math easy so you could learn something. Really what I should do is probably put a constant term in here or something, but whatever. Is everybody okay with that? This is a nonsense problem, but the mechanics that we went through were supposed to help you learn. And I tried to pick an easy one. I couldn't make it easy and meaningful. Yeah, it's actually more like, yeah, I don't want to go into it. If you care about that, you can talk to me later. Is everybody okay with that? We learned from it. If you have a function, you could shove it in there and integrate it and learn it. To help you practice that, 7.8, you could do that one at home. There, it's you could say like, boy, this seems pretty silly. That's an example of how it might relate to electronics. So if you want to know about quantum mechanics, electrical engineering, things like that, it's foreshadowing that type of work. And be careful. One of these, I think when you stick in the 0 limit, remember that was kind of my my pet peeve here was make sure you always check the 0 limit. I believe in 7.8, it's an example where if you plug in x equals 0, it doesn't just magically vanish. Okay. Okay. All right. One last topic. We got 10 minutes. All right. Power. Page 8. All right. Now, before we even start, I want to give some symbol review here. And the ways I write these letters. you may not realize this, but we're gonna have 4 major letter P looking symbols. It's important that when we're writing symbols, we pay attention to the way we write them. Here is one example why. Capital P that's bubbly, I'm going to call power. This symbol, which looks like a P, is not a P at all. It's a rho because it's a Greek letter, and that means density. Lowercase p for us is going to be momentum, something we learn about in chapter 9. Uppercase P is going to be pressure. We learn about that in chapter 14. So even though it seems absurd that I'm going to start writing this weird bubbly looking P, that's just my way of keeping these problems straight. In some problems, they literally all 4 appear. Gnarly. So we got to keep our letter P's straight. Is everybody okay with that? Just the symbol? Yes.
What if you just use the letters at that point?
What's that?
What if you just use the letters at that point? You just like spell it out, like power.
Yeah. So this is a good point. If it's confusing, there's no rules about writing the whole word out. And in particular, in a code, that's why you write out a good variable name. Because sometimes it makes more sense to just write out the word than have to explain yourself. But since I like talking so much, I like to keep all these letter P's because that keeps me employed. Are you good with that?
Yeah.
All right, yeah. Just making fun of myself. All right, enough on that. So that's just the letter P's. Power is dE dt. Change in energy over change in time. What are the units? Help me out. What's the unit of energy that we've been talking about all day? It's a real gem of a unit. The joule. Okay, so we got a joule per second. That's equivalent to what unit? What? Yeah, that's the unit. What? Okay. A watt is a joule per second. What? Okay. I really enjoy that joke. I don't know why. I'm still happy inside. All right. A watt is a joule per second. All right. Now, in this case, there's oftentimes 2 other equations that we might relate this. Change in energy. Have we talked about anything today that's related to change in energy? Work. So sometimes what you'll see is the average power is equal to work over time. And finally, one last way of writing this, we'll see that power instantaneous at any one instant. So this is the average power, is the total amount of work over the total time. Instantaneous power is given by force dot velocity. Now this probably seems reasonable because think about it. Work is force dot distance, or dot displacement, I should say. Well, displacement over time gives you velocity. We're back. Did that make any sense at all? Again, there's a force times displacement up here. You divide that by time, it's force dot velocity. Okay. Now we got 5 minutes. Let's do the best we can to get through this. I want to look at 7.10. I really like this problem, and I think we can actually do it. Okay, 7.10. X of t is equal to 2.00 minus 3.00 t squared, I think. T cubed, okay. Before we get started on this problem, I'd better know the units of these numbers. What are the units of 2? Meters. What are the units of 3 in this problem? I need to cancel out 3 seconds. So it's going to be meters divided by seconds cubed. Do you see that?
Yep.
Going to do that again, right? This is in meters. Divide through by those 3 seconds, I get meters per second cubed. Okay? Okay, tell me the velocity real quick. How do you get velocity from x? Derivative. So what do I get?
-9t squared.
What are the units on this 9? What were the units on the 3? Meters per second cubed. When I bring down the 3, is that going to
It's
change
supposed
the
to be
units?
t squared, by the way.
T squared. Yes, I was testing it. Nice job. Thanks. When I bring down the 3, is that going to change the units? No. So this is also meters per second cubed. Does this make sense? Second squared times meters per second cubed gives me meters per second. What's the acceleration? Number the derivative. What are the units on this? It's the same, right? Think, when I multiply by seconds, I get meters per second squared. It works out. Everybody okay with the units and this? Now, I happen to know in this problem, it says the mass is 0.250 kilograms. How could I get the force as a function of time? F equals ma. Do you know m? Do you know a? It's negative 4.50 t, like that. What are the units? It was this number, which had meters per second cubed, times this number. So now what are the units? Kilogram meter per second cubed. Everybody see that? Okay. Now here's the deal. Up till now, everything you have already done in lab. You did this on your first presentation. Do you remember that? Think carefully. You guys made videos of something moving around. Then we dumped that stuff in and we tracked it. In theory, you could punch that into Excel and ask it to get this for you. You could say, get me the trend line. So think about this. If you took a video of something and marked its position, you could get X of t. From that, you could get the velocity, the acceleration, and if you knew the mass of it, also the force. All of this is stuff you could do with an iPhone and any object in the world. If I wanted to understand the power, how could I get the instantaneous power? If I want the instantaneous power, what was the equation for it? Force dot velocity. Do I have those two things? Yeah, it would be negative 4.50 t times negative 9.00 t squared. Now think carefully. Does a positive answer make sense here, right? Is this force trying to speed this thing up or slow it down? The force is negative. The velocity is also negative. Is the force helping it go in the negative direction or not? They're both negative. This makes sense. So the power is positive, right? So there's some sort of power input, which is making it go faster. That's why the speed is increasing. All right. At this point, you could take any value you want for time, and we've got the power at that one instant. Or if we wanted to get the power on average, just watch the subtle difference, and I swear this is the last thing I'm going to do to you today. We're going to get out on time. Power average is, well, I could do 1/2 mv final squared minus 1/2 m the initial squared divided by the time. Now, you might be saying, wait a minute, dude, where did you get that from? Can you tell me where to get that? Delta K is the work. So remember, this up here, all of that is the same thing as work equals the change in energy. So it's just different ways of writing this. Now, what's interesting is at any one instant, the powers this complicated function is nonlinear. We could get the average power by saying, what's the final speed? What's the initial speed? How long did it take? And you punch it into this formula and you'll get a different answer. This is a good number if you want the average. That's a good number if you need the power at one specific instant. Got it? There's a couple other problems you could do here. For example, all the problems on that page are pretty good. And we're done with chapter 7 for the most part. I know it's 1 minute over. Let me say this. Basically, we're done with chapter 7. We're moving on to chapter 8 next time because chapter 8 is going to revisit this stuff and we're going to do it in a slightly different way. So even though it feels like, man, we just went through that chapter really fast, I'm going to review a lot of this in chapter 8 as well. So chapter 7 and 8, I kind of treat like one mega chapter. All right, so if you haven't already turned in your labs, get that done. If you forgot to do that, get that done. I'm going to stop the live stream and then any questions if you want. Oh.